A machine switches on, and by breakfast, the price of the future has changed. Not the stock market first, not geopolitics first, not even climate headlines first. The first shock is simpler than that. Screens light up in trading floors, control rooms, military offices, data centers, and apartment kitchens with the same impossible sense. Commercial fusion is real, and it works now. Not in a laboratory in the very narrow way. Scientists usually mean works. Not a one-off physics milestone buried under 27 footnotes. Not a reactor that almost breaks, even if nobody asks difficult engineering questions. This time, it is a machine that runs, produces steady electricity, breeds its own tritium, survives the neutron damage long enough to matter, and sends power to a grid at a price utilities can actually use. And one question begins to stalk the planet before lunch. If humanity has just learned how to build a star in a box, what exactly happens to a civilization that has spent 2 centuries organized around energy being expensive, uneven, and politically dangerous? To understand the size of that question, the script has to start with an uncomfortable truth. Modern life is basically fossil fuel architecture with Wi-Fi. The world's cities glow because coal, gas, oil, hydro, wind, solar, and fission are stitched together in a giant nervous system that never fully relaxes. Every air conditioner, factory robot, AI server rack, train line, smelter, and hospital ward depends on electricity arriving at the right second. When it does not, modernity becomes weirdly fragile. That fragility is growing. Electricity demand is climbing as more transport goes electric, more industry gets cleaned up, and more computation moves into giant data centers. The International Energy Agency says global electricity consumption from data centers could roughly double to around 945 terawatt-hours by 2030 in its base case. That is not a side story. That is a warning flare from the future. Humanity is asking for more power in more places, more reliably, than the old system comfortably wants to give. Fusion has always looked like the escape hatch. The physics is absurdly attractive. The IA explains it simply. Light atomic nuclei fuse into heavier ones and release enormous amounts of energy. The most discussed fuel pair is deuterium and tritium. Deuterium can be extracted from water. Tritium can be bred from lithium. In theory, the deuterium in a liter of water could produce as much energy as burning about 300 liters of oil. ITER goes even further. Fusion releases nearly 4 million times more energy than a chemical reaction like burning coal, oil, or gas. It is the kind of comparison that sounds fake until physics ruins everyone's sense of scale. But this is why fusion has spent decades living in the frustrating kingdom of almost. The fuel must become plasma hotter than 100 million degrees Celsius. That plasma must be controlled long enough to do something useful. The neutron's hammer reactor materials. Heat has to be removed without wrecking the reaction. Tritium has to be bred and recycled. Maintenance has to be done with robots inside an environment that treats ordinary hardware like tissue paper. In 2024, the National Ignition Facility achieved fusion ignition again, with one shot producing 5.2 megajoules from 2.2 megajoules of laser input. Scientifically, that was historic. Commercially, it was still not the same thing as running a power plant for cities, and yet the world kept moving toward it. The Fusion Industry Association reported more than 45 private fusion companies in its 2024 survey, over 4 zero-zone employees, and total industry investment above $7.1 billion. Nearly 89% of surveyed companies still expected fusion electricity on the grid by the end of the 2030s. The money was not just buying physics anymore. It was buying a place in a possible new energy order. Then tomorrow arrives early. A company, or maybe a state-backed consortium, unveils the first reactor that does what every skeptic demanded. It runs continuously enough to matter, survives long enough to finance, and produces power cheaply enough to start a queue. There are live feeds, independent verification, utility contracts, and the most beautiful sight in industrial history. Bored grid operators treating fusion like just another source of electricity. That boredom is revolutionary. At first, ordinary people underestimate it. That is what humans do with slow-burn miracles. They underestimated the internet because it sounded like email. They underestimated smartphones because they looked like smaller computers. They underestimated AI because it first wrote average poetry. Fusion will be underestimated because on day one, most people do not receive a spaceship. They receive a news alert and go back to work. But personal consequences begin almost immediately. Homeowners in blackout-prone regions start hearing a new promise from utilities: stable baseload power without coal smoke or imported gas. Apartment renters hear another promise: cheaper electricity eventually. People who have spent years timing laundry to off-peak prices start asking a dangerous question. What if electricity becomes boringly abundant? What if charging a car, cooling a home, heating water, and running an AI assistant all night stops feeling like a tiny economic decision? That sounds liberating. It is. It is also psychologically destabilizing. Scarcity is one of the invisible teachers of human behavior. It teaches timing, trade-offs, and limits. If power becomes dramatically cheaper, daily life changes in subtle ways first. Buildings are cooled more aggressively. Urban farming gets another look. Personal robotics suddenly make more sense. Households that once thought in kilowatt hours begin thinking in possibilities. And that is before prices actually fall very far. Expectations move faster than infrastructure. Fortunately, expectations are about to outrun reality. The first real earthquake is economic. Energy is not just one sector. It is the hidden cost inside every sector. If a fusion plant can provide constant low-carbon electricity at scale, then the economics of making almost everything begin to wobble. Data centers stop hunting only for cold climates and cheap gas. They cluster near fusion hubs. AI companies desperate for steady power sign decade-long offtake deals in hours. The race to build bigger models stops looking like a software contest and starts looking like an energy land grab. Then heavy industry feels the tremor. Steel, cement chemicals, fertilizer, and hydrogen all depend on energy so intensely that small price shifts can reorder entire supply chains. Cheap electricity makes green hydrogen more plausible. Green hydrogen changes the math for steelmaking, shipping fuels, ammonia, and synthetic aviation fuel. Desalination becomes less painful in water-stressed regions, and that matters more than it sounds. When energy gets cheaper, dry places become more negotiable. Coastlines that were once hemmed in by water scarcity begin sketching new futures in concrete and glass. But cheap power was not the biggest shock. The biggest shock was location. For more than a century, industry is clustered around fuel deposits, ports, pipelines, river systems, and old grid patterns. Fusion does not erase geography, but it weakens some of its oldest rules. If fuel can come from deuterium and bred tritium rather than endless trainloads of coal or fleets of LNG, carriers, industrial maps start to loosen. Nations that import energy see strategic daylight for the first time in generations. Nations that export fossil fuels see a different sunrise entirely. This is where the scenario turns political. Oil and gas do not vanish tomorrow. The world owns too much combustion equipment for that. But markets price the future, not just the present. If investors start believing that fusion can scale over the next 2 decades, long-term fossil projects become harder to justify. Pipelines expected to pay off over 30 years suddenly look like expensive nostalgia. Petrostate budgets, sovereign wealth plans, shipping routes, and military doctrines all begin to absorb the same poisonous uncertainty. What if the commodity that built this nation stops being civilization's irreplaceable bloodstream? Some countries respond with speed. They pour money into domestic fusion manufacturing, superconducting magnets, advanced materials, robotics, grid expansion, and power-intensive industry. Others respond with denial, lobbying, and strategic delay. A few try to weaponize the transition itself by locking up supply chains for lithium, specialty metals, precision components, or tritium handling expertise. That is when the future stops looking like a clean science story and starts looking like every technological revolution humanity has ever had, only bigger. And then comes the next twist. Fusion works. Deployment does not. The planet discovers the oldest rule in engineering. A breakthrough in principle is not the same as abundance in practice. Even if one reactor design works tomorrow, civilization cannot print 10,000 of them by next Tuesday. Factories must be built. Supply chains must be certified. Operators must be trained. Regulators must learn what exactly they are regulating. Grids must be expanded to move all this new power where it is needed. Transformers, high-voltage lines, cooling systems, robotic maintenance platforms, shielding materials, and replacement components become the new choke points. The world has solved the physics problem just in time to collide with the manufacturing problem. That gap creates the major crisis. Not an energy shortage exactly, but an expectation shock. The public hears limitless clean energy and assumes the old economic pain should disappear immediately. Bills should fall. Factories should return. Water should be cheaper. AI should be everywhere. Governments, sensing opportunity, make extravagant promises. Markets front-run reality. Bubbles form around fusion-adjacent companies, industrial land, and future power contracts. Scams multiply. Political slogans get ahead of engineering schedules. Humanity begins fighting over an abundance that has not been built yet, and something darker happens in parallel. Regions whose revenues, social contracts, or strategic importance depend on fossil exports feel the floor move beneath them. A country can survive lower oil demand. It struggles more with lower oil relevance. If leaders believe fusion threatens national stability, they may not react gracefully. They can subsidize old systems, trigger price wars, intensify regional conflict, or attack the credibility of the new technology itself. Some may sabotage supply chains. Some may lean harder into petrochemicals and plastics. Some may simply refuse the future until the future arrives anyway. Inside fusion countries, another conflict ignites. Who gets the first cheap electrons? Cities, industry, AI firms, desalination plants, hydrogen projects, rural grids? Voters may discover that abundant energy still has a waiting list. Utilities prefer stable, giant customers. Politicians prefer visible household wins. Militaries prefer secure supply. Tech giants prefer dedicated capacity. Everybody has a perfect argument. Not everybody gets the reactor first. This is the emotional peak of the story because fusion's greatest promise now creates a very human problem. Once scarcity starts to break, power becomes even more politically valuable, not less. The first nations to scale fusion are not just selling electricity, they are selling strategic immunity. That is enough to make allies nervous, rivals aggressive, and bureaucrats suddenly poetic about national destiny. Humanity adapts the way it always does, messily competitively, and faster than expected once money gets scared. Governments launch emergency industrial policies. Permitting rules are rewritten. Engineering schools become strategic assets. Old shipyards are converted into reactor module factories. Ports once designed for LNG imports are redesigned to receive superconducting components, shielding materials, and massive prefabricated energy systems. Robotics firms that once built warehouse machines now build maintenance units for high radiation environments. The labor market mutates in plain sight. Some adaptations are elegant. Fusion pairs with renewables rather than replacing them outright. Solar and wind still make sense where they are cheap and fast. Batteries still smooth peaks. Hydro still stabilizes regional grids. Fusion becomes the deep backbone, the source that keeps running when clouds roll in, wind slows, and demand spikes at the exact wrong moment. The smartest energy systems are not ideological, they are hybrid. Other adaptations fail spectacularly. Some countries rush immature reactor designs into deployment and discover that commercial does not mean idiot-proof. Some utilities overpay for early projects. Some cities build around promised power that arrives 5 years late. Some governments discover the word nuclear still triggers public fear even when the engineering profile is different from fission. Fusion may be safer in several important ways, but politics does not run on neutron diagrams. It runs on trust, headlines, and whether voters think someone is experimenting near their children. Still, the momentum continues because the incentives are too large. Cheap constant electricity makes carbon removal more plausible. It makes fertilizer and clean fuels easier to produce. It makes desalination, recycling, and industrial heat more affordable. It gives energy-poor nations a path that is not permanent dependence. And most importantly, it changes the strategic meaning of distance. Remote regions with harsh climates, weak wind resources, or thin fuel access can suddenly support more industry, more cooling, more compute, more life. By the 2040s, the visible world begins to look different. Nighttime satellite images show new clusters of light in places that used to dim after sunset. Desert edge cities run vast desalination systems and inland pumping networks. Industrial parks hum beside compact reactor campuses wrapped in shielding, robotics bays, and turbine halls. Former coal regions reinvent themselves as fusion manufacturing corridors. Ports that once smelled of crude now move advanced ceramics, magnets, and modular power hardware. Daily life changes too, though not in the cartoon way people first predicted. Electricity does not become free in some magical sense. Nothing involving concrete, copper, labor, and politics is free. But energy stops being the central pain point in more decisions. Homes are better cooled and heated. Electric transport spreads faster. AI assistants become more embedded in everyday work because compute is easier to feed. Water recycling becomes normal. Vertical farming works in more places. The background stress of running civilization on constrained power eases, and that may be one of the most underrated luxuries in human history. There are downsides. When people feel energy-rich, they often become energy-sloppy. Efficiency loses some of its moral glamour. Jevons paradox, the old idea that improving resource efficiency can increase total consumption, returns wearing a futuristic suit. Humanity may use fusion not just to clean up old systems, but to build absurd new appetites. More compute, more cooling, more extraction, more manufactured environments, more everything. Abundance solves some problems by creating room for larger ones. And then civilization notices the biggest consequence of all. Fusion is not merely a cleaner power source. It is a force multiplier for every other frontier technology. AI, advanced manufacturing, synthetic biology, carbon capture, water systems, robotic mining, even space infrastructure all become easier in a world where clean electricity is more available. A civilization with cheap energy can afford to experiment more, automate more, purify more, recycle more, and recover more from its own waste streams. In other words, fusion does not just power the future, it speeds the future up. That acceleration produces a strange emotional shift. For generations, modern societies were trained to think in terms of limits. Limited fuel, limited land, limited carbon budget, limited grid capacity, limited political patience. Fusion does not erase limits, but it changes which limits matter most. Energy becomes less central. Coordination becomes more central. Wisdom becomes more central. A species that can power almost anything now has fewer excuses for what it chooses to do. So if fusion energy worked tomorrow, the world would not become a utopia by the weekend. There would still be bottlenecks, conflict, inequality, hype, sabotage, delays, and all the familiar human talent for turning miracles into paperwork. Oil would not vanish. Renewables would not disappear. Governments would still mismanage things. Markets would still panic. Some places would benefit first. Others would wait too long. The first era of fusion would feel less like a heavenly sunrise and more like the opening of a new industrial age. Loud, uneven, full of winners, losers, and unintended consequences. But beneath all that noise, something genuinely historic would have changed. For the first time, humanity would possess a credible path to large-scale energy abundance without building civilization on combustion. That would alter economics, strategy, climate politics, industrial geography, and even private psychology. The ceiling over human development was never just made of physics. It was also made of engineering, institutions, and belief. And that leaves one final question hanging over the century. If energy stops being the main thing civilization cannot afford, what excuse does civilization have left? Please subscribe my channel.